Hello and welcome to Empowered Learning. This video will be about taking the derivatives of inverse trigonometric functions and also showing how we use implicit differentiation in order to derive inverse trigonometric functions. The first thing I wanted to do here before we actually get into some of these examples here is to remind you what the graphs of some of these basic inverse trigonometric functions look like and also what the domain and range of them are. So the importance of this is whenever we take the derivative of a function, what we're actually trying to do is track the rate of change of that function, or put another way, we're trying to track the slopes of the tangent lines. So one of the things that may help you out in trying to remember what these derivatives are is what the sign of them should be. In other words, for valid values of x that you plug into these inverse trig function derivatives, should your result be negative or should it be positive? And also, you need to know for what values of x, again, you can actually use for these derivatives. So let's take sine inverse for example. So if you notice, sine inverse is a function that is always increasing. So whenever you find the derivative of sine inverse, and you're, let's say, computing it for some value of x, in this case, that's going to be in between -1 to 1, then one of the things that you know is that the derivative of this function itself is always going to be increasing. So if we were to draw the graph of the derivative of sine inverse of x, it would be a graph that's always increasing because of that. So similarly, if we look at cosine inverse, we see that this graph is always decreasing. So since it's always decreasing, we know that its derivative is going to have to be negative regardless of what values of x we plug into. Okay. Now, if you are wondering how in the world am I supposed to remember what these graphs look like so that you'll know what the domain and range are, you could check out my videos on actually sketching the graph of inverse trig functions. And so I have some, I think for sine inverse, cosine inverse, and maybe one or two of the reciprocal inverse trig functions as well. And so I go through the basic idea of taking let's say for sine, I'll take sine and we'll restrict the domain of sine in between -pi/2 and pi/2, because that will force sine in that particular range of x values to be a 1-to-1 function. And then from there, we would interchange all the x and y coordinates to come up with the inverse functions graph. And so what you see for sine inverse here would be just that. Now, of course, for the reciprocal ones, there's another step that's involved. So for instance, let's say for secant. So to take the derivative, well, to produce the graph of secant inverse, what you would do is use the graph of cosine to come up with secant. And to do that, you would just basically take wherever you have x-intercepts for cosine and make those vertical asymptotes. And then after that, for each portion that's within each vertical asymptote, you would just flip it. And that's kind of what you'll be doing whenever you take the reciprocal of it. So, of course, at the peaks and dips, the points, let's say 0, 1, and let's say pi, -1, those points will stay the same, but all the other ones will flip. And then from there, we would have to cut the graph of secant, or restrict the domain of secant in between 0 to pi, so that we could interchange all the x and y values and again come up with the inverse function. So again, this is what you'll see. So I'm just mentioning that so that you know that there is a way to remember this stuff without you necessarily having to memorize it. So check out those videos if you have the time. So again, the main thing I want to do here is just call these graphs to your attention, and I'm going to refer back to these whenever we get to the end of this video, when we start, video series, whenever we start to derive inverse trigonometric function derivatives. And you'll see why having these graphs here and knowledge of them are important. Now, also wanted to just remind you here of some of these identities as well. So for our inverse cosecant, we know that's the same as sine inverse of 1 over x. For secant inverse, it's the same as inverse cosine of 1 over x. And for inverse cotangent, it is pi divided by 2 minus tangent inverse of x. And so, of course, for cotangent, we can also look at it the piecewise function way as well. So the main reason I'm bringing this up is because for most of you, if you're dealing with a calculator, you do not have a secant inverse, cosecant inverse, or secant inverse, or cotangent inverse button on your calculator. So in order to figure out, let's say, what cosecant inverse of 1/2 is, you would have to put it like this in your calculator and actually say, what is sine inverse of 2? Because the reciprocal of 1/2 is 2. So that would would be a way in which you would have to do that. So yeah, so that's that's the point of that. All right, so let's go ahead and move on here to some examples. All right, and before we do, again, I just wanted to show you these other inverse cofunction identities as well. You may want to jot these down. All right, so before we go to these examples here, one of the things I want to make sure that we understand is the difference in between the trigonometric derivatives and the inverse trigonometric derivatives. So for, of course, our regular derivatives here, we see that the derivative of sine is just cosine, derivative of cosine is negative sine, and derivative of tangent is secant squared. And of course, we also see here that derivative of cosecant is just negative cosecant cotangent. Derivative of secant is secant tangent, and the derivative of cotangent is negative cosecant squared. And of course, the derivatives of sine and cosine, we can actually derive those by doing the limit of the difference quotient. But then afterwards, the derivative of tangent, cosecant, secant, and cotangent can all be taken by utilizing the quotient rule and deriving those derivatives from there. What our focus is the inverse trig functions, which end up like this. And so we'll see later on here that we can actually derive these by thinking of sine inverse of x as an angle, because it is an angle, because that's what the inverse of a trigonometric function is. It is an angle. And so we'll look at it that way and see how we derive some of these. But we'll see here, tangent inverse of x is just 1 divided by square root of 1 minus x squared. Derivative of cosine inverse is same thing as sine, but you see that it is negative. Okay, so negative 1 divided by square root of 1 minus cosine x. For tangent inverse, it's just 1 divided by 1 plus x squared. For cosecant inverse, it's just negative 1 divided by x times x squared minus 1. And I want to make sure that we understand that even though it's not written here, this should actually be an absolute value of x. And here should also be an absolute value of x2. And you'll see that once we actually derive it. Okay. For secant, of course, we have same thing as same as cosecant inverse, but you see that it ends up being positive instead of negative, like how cosecant inverse is. And then cotangent inverse, the derivative of that is the same as tangent, it's just negative. Okay. So we're going to use these facts to do some of the examples here and take some of these derivatives. All right, so for our first example here, we want to take the derivative of sine inverse of 2x plus 1. And of course, my hint here is just basically saying that this is an inside function here, so we're going to have to employ the chain rule. So since I've put this here, let's go ahead and use it. So if we do the derivative of y with respect to x, that will be the same as derivative of y with respect to u times derivative of u with respect to x, where my u is just going to be 2x plus 1. So here we know that this will now look like sine inverse of u times derivative of 2x plus 1. And so for sine inverse, we know that the derivative of sine inverse is just 1 divided by square root of 1 over u squared. And the derivative of 2x plus 1, all that will just be 2, because derivative of 2x is just 2. Derivative of 1 is 0. And so from there, that'll just be 2 divided by square root of 1 minus, and of course our u is 2x plus 1, and that will be quantity squared. Okay. Now, we'll go ahead and try to do what we can to simplify that now. And of course, if we FOIL out 2x plus 1 quantity squared, that would be 4x squared plus 4x plus 1. And notice here that'll be 1 minus 4x squared minus 4x plus 1. Oh, sorry, minus 1. Let's get rid of that. And of course, these 1's here will cancel to 0. And what we will have left here is square root of, and I'm going to go ahead and factor out the 4 that is in both of those. So it'll be 4. Let's just try that over again. So that'll be square root of 4 divided, so 4 times minus x squared minus x. Of course, here we know that the square root of 4 that's in here, that could be factored out. And we just have this. And the square root of 4 is the same as 2, so all that reduces to 1. And our final answer here will just end up being 1 divided by square root of x squared minus x, or negative x squared minus x. And that would be our final answer here. All right, so let's move on to our second example. So in this example, we see that we're trying to take the inverse of arcsine, or tangent inverse, put it another way, of 1 minus x over 1 plus x raised to the 1/2. So here again, we're going to have to use the chain rule. So for this one, let's say the derivative of y with respect to x. We'll just do this without writing the whole Laplace notation thing. We know that all of this here is going to be the inside function. So when we take the derivative of tangent inverse of blah, that is just going to be 1 over 1 plus blah. And our blah here would be 1 minus x over 1 plus x, all that raised to the 1/2. And of course, blah will be squared. So that's derivative of the derivative of tangent inverse of blah times, now we need to do the derivative of the inside function itself. And of course, that will entail us doing the quotient rule and chain rule when necessary. So if we take care of this first factor, we know that from our exponential rules, anytime we have something raised to a power and then that's raised to another power, we can multiply those exponents. So we just have 1 over 1 plus, and in the second term, 1 minus x over 1 plus x. And so now we'll take care of the derivative of this. And using the chain rule, we know that the derivative of blah raised to the 1/2 is 1/2 times blah raised to the negative 1/2 times, now we have to do the derivative of the inside function. And of course, our inside function would require that we use the chain rule. Sorry, the quotient rule. All right, so for this first factor, talking about this, I'm going to multiply the numerator and denominator by x plus 1 to get rid of this fraction here. So if I do that, I get x plus 1 in the numerator over, and then in the second term here, that would be in x plus 1 plus, and then the 1 minus x over 1 plus x times x plus 1, that would just end up being 1 minus x, because I have x plus 1 in common. All right, so I've went ahead and written in the x plus 1 being multiplied times the numerator and denominator so that everyone could follow what I was doing here. Of course, you'll see in the numerator just 1 times x plus 1 is just x plus 1. In the denominator, this second term here, this x plus 1 is considered to be in the numerator of a fraction. So these two x plus 1s here reduce to 1, and that's how we get the x, 1 minus x there. So I want to make sure that that was clear. All right, so moving on, we're going to now go ahead and deal with this derivative here. All right, so first things first, let us go ahead and write the 1/2 times 1 minus x over 1 plus x raised to the negative 1/2. And so now to deal with the derivative of this, we will be using the quotient rule. So the quotient rule says we'll take the low function times derivative of the high function minus high function times derivative of the low function, and all that over the low function squared. And of course, we know that for 1 minus x, if we take the derivative of that, that will just be negative 1. And if we take the derivative of 1 plus x, that will just be 1. So of course, all of this would just be 1, and all of this would just be 1. So make sure I put our equals there. So where that leaves us is as follows. Of course, this x and this minus x cancel to 0. So what I end up having is x plus 1 over 2, and multiply with this 1/2, that'll give me x plus 1 over 4. Now multiply that times 1 minus x over 1 plus x raised to the negative 1/2. And here we have, this is a minus 1, not a 1, because the derivative of negative x is just negative 1. So if we do that, then 1 plus x times a negative 1 is just minus x minus 1 minus x. And we also have this minus of x minus 1 here. So if we distribute that negative, that would be a minus 1 plus x. And all of that will be divided by 1 plus x quantity squared. And again, this minus x and x cancels to 0. And our minus 1 and minus 1 here will simplify to a negative 2. So we have x plus 1, and I'm going to bring that negative 2 over. And then we have 1 minus x over 1 plus x, all that raised to the negative 1/2 times 1 over 1 plus x quantity squared in the denominator. And of course, this would just simplify to negative 1 over 2. So at that point, we'll also see that this x plus 1 and this 1 plus x squared, that would just simplify to just 1 here. And this would just give me 1 plus x left. So let me scroll down, and now we'll see what the results of all that is. So if we keep on going here, in this first factor, I just have a negative 1 over 2. In the second factor, this is basically going to be 1 over square root of 1 minus x over 1 plus x. So I'll write it like that and then rewrite it the other way that I want. And here we have a factor of 1 over 1 plus x that's left. And so we know that 1 over square root of 1 minus x, 1 plus x, that's just a reciprocal. So we could rewrite this as square root of 1 plus x over 1 minus x times 1 over x. And so we see from there that this square root that we see here over everything, we could just write that over each the numerator and denominator separately. Just do it like this. And from there, we know that this is the same as 1 plus x raised to the 1/2, and this is 1 plus x raised to the 2/2. So if we did this, this part would go to 1, and this part would end up going to this square root of 1 plus x. And then we know that square root of 1 plus x and square root of 1 minus x could combine together to be square root of 1 minus x squared. And then, of course, we still have that 2 that's there. And after all that work, we finally have arrived at what our formula for our derivative would be. And we see that it's a relatively simple expression, but we had to do a lot of work to get there. Okay? All right, so let's move on to our next example. All right, so we see that we want to take the derivative of secant inverse of 15x raised to the 9. So of course, 15x raised to the 9 is our inside function, so we'll be using the chain rule here. If you recall, the derivative of secant inverse itself is just 1 over absolute value of x times square root of x squared minus 1. And so wherever we see this x here, we're going to be replacing it with 15x raised to the 9. So let's go ahead and perform that now. So if we take the derivative of this, we know that the derivative of secant inverse of blah is just 1 over absolute value of blah times blah squared minus 1. So that is the derivative of the outside function with respect to blah times, now we're going to take the derivative of 15x raised to the 9 with respect to x. Okay. So in doing that, we know that the derivative of 15 times x raised to the 9, we'll start off having to multiply 9 times 15 per the power rule. That would be 135, and then we subtract 1 from the exponent, so that'll be 8. And then of course, if we kind of look at what we can plug in here for secant, secant inverse here, one of the things that we know is that our result here has to end up being this absolute value of x here. And I'll go back to those graphs to show you what I mean by that. So if we go back, as you can see here, the graph of secant inverse here is always increasing because the slopes of the tangent line are always positive. So we have to make sure that we have positive answers, even though there are some negative values of x that we can plug in here. So understanding that, let's go back to this example here. What I'm going to do is rewrite this absolute value, and I know that I can split up absolute value of 15 times x plus 9 is just absolute value of 15 times absolute value of x raised to the 9. And of course, absolute value of 15 is just 15. So I'm just going to write that. And for this x raised to the 9 part, I could rewrite that as absolute value of x to the 8 times absolute value of x. And so we know that x raised to any even power is always going to give us a non-negative answer. So this part we can just simplify to just x raised to the 8th. But here we have to keep that absolute value of x there. So we're going to rewrite 15x raised to the 9 as 15x raised to the 8 times absolute value of x. And then we'll go ahead and write in the rest of this. 15x raised to the 9 squared minus 1. Okay. And so from there, that should make doing some of the simplification that we need to do a little bit more simple. So let's move on from here. Now, of course, 135 divided by 15 is 9. And we know that x raised to the 8 divided by x raised to the 8th reduces to 1. So here we just have 9 divided by absolute value of x times 15x raised to the 9 quantity squared minus 1 here. And I'm trying to think if we want to do anything else with that. It may not be worth it. So one of the things that we can do here is if we want to go ahead and square that 15x raised to the 9, that portion will just end up being 225x raised to the 18 minus 1. But again, not anything that is going to help us simplify anything. So if you wanted to keep it in this form, you could very well do that. The only other thing I could think of, and this is just getting kind of fancy here, is that we could factor out a factor of 225. If we did that, then this would be square root of 225. And what would be left under here is x raised to the 18 over 1 over 225, like that. And of course, square root of 225 is just 15. And if we take 9 divided by 15, both of these have a factor of 3. So 3 would go into 9 3 times, and 3 would go into 15 5 times. You could rewrite this way if you saw fit. Oops. Let's make that look a little better. Yeah, so you could do something like that, and of course there would be a 5 here. So you could rewrite it this way. I know personally I would probably stop here, or maybe even here, but if for some reason you need to go further, then you could do this. And if for some reason you need to have everything in terms of everything being squared, you could just rewrite this again as x raised to the 9 squared minus, and of course 1 over 225 is 1 over 15 quantity squared. So you could write it like that as well. Just depends upon what your application is for this derivative, but I would just say for test, if you're trying to calculate it, I think this form or this form would be acceptable. All right, so let's move on to example D here. And so we're asked to calculate the derivative of cotangent inverse of square root of x squared minus 1 plus secant inverse of x. So again, for cotangent, we know that the derivative of cotangent inverse is just going to be the negative of tangent inverse, which is just going to be negative 1 over 1 plus x squared. So of course, everywhere where we see x in the derivative of cotangent inverse, we're going to replace that with square root of x squared minus 1. And since, of course, this is a composition function here where square root of x squared plus 1 is the inside function, we would have to perform the chain rule whenever doing the derivative. For secant inverse, just like how we just got through talking about, the derivative of that is just 1 over absolute value of x times square root of x squared minus 1. So let's go ahead and calculate. And of course, we're noticing here that x has to be greater than 1 to be able to calculate this. And we'll see why that is here at the end. Okay, so let's move forward here. So the derivative of cotangent inverse of blah is just negative 1 over 1 plus blah. And our blah is just square root of x squared minus 1 squared. And then, of course, that will be the same as the derivative of square root of x squared minus 1, which will just be the same as saying, let's take x squared minus 1 raised to the 1/2 and take the derivative of that with respect to x. And we'll take care of that in the next step. So plus, now let's do the derivative of secant inverse of x, which is simply just 1 over absolute value of x plus 1 times square root of x squared minus 1. Okay, so from here we need to take the derivative of x squared minus 1 raised to the 1/2. So let me just go ahead and write the rest of this information down. And we know that the square root of anything squared is just that same thing. We just lose the radical sign there. If we take the derivative of x squared minus 1 raised to the 1/2 using the chain rule, that'll be 1/2 times x squared minus 1 raised to the negative 1/2. And then we'll multiply that times the derivative of x squared minus 1. And we'll keep the second term the same. Okay. Now, looking at our first term again, we know that this 1 and that negative 1 would cancel to 0. And this 1/2 that's up here, we can move the 2 down. in the denominator. So now we would have in our denominator here 2x squared. In our numerator, I'm just going to write this again, x squared minus 1 raised to the negative 1/2. And the derivative of x squared minus 1 would just be 2x, because the derivative of x squared is 2x. The derivative of negative 1 is 0. And so those two terms here, that will go to 1, and that will just leave us with x there. And then, of course, then we have plus 1 divided by absolute value of x times square root of x minus 1. So when we look here, and let me make sure I bring down this negative here. So I had it here. Oops. Yep, I had it here, had it here. Need to make sure I bring it here. So when we come here, this will be minus, and this square root of, in this x squared minus 1 raised to the negative 1/2 is the same as 1 over square root of x squared minus 1. And of course I have another x that's down there. And here, this is same here. Now, if you notice, we said that x had to be greater than 1. And so because x has to be greater than 1, any value that we plug into this absolute value here, absolute value of x would just be x for values that are greater than 1. So this part here just simplifies to just simply x. And in looking at it that way, we see that this first term and the second term are direct opposites of one another. And because of that, this result here is 0. So what this is telling us is that if we take our cotangent inverse of square root of x squared minus 1 and add secant inverse to it, then what we essentially get for all values of x that are greater than 1 is a horizontal line. And we know that because the derivative ends up being 0, which tells us that the slope of the tangent lines for all values of x greater than 1 are going to be 0. And horizontal lines are type of functions that have a derivative of 0, or horizontal lines are the types of functions that have tangent lines that have a slope of 0. So that's what we see here in this example. All right, so for this next example, you'll see that I actually have worked this one out, and you see how we have the sine inverse of 6x raised to the 4th in there. And we're going to be doing a combination of the product rule and the chain rule to find the derivative of this. So if we start off, the first thing I do is just change the square root here to just 1 minus 36x to the 8th raised to the 1/2. And I'll also note that in my next step here that I'm going to be doing the chain rule to this. So I look at 6x raised to the 4th as the first function and sine inverse of x raised to the 4th as the second function in the product rule process. So here I'm taking the derivative of the first times the second plus first times derivative of the second, where this is the first and that is the second function. Now for this term, we know that we'll just simply be using the chain rule, where we're looking at the outside function as blah raised to the 1/2. So the derivative of that is 1/2 blah raised to the negative 1/2 times the derivative of the inside function. And so from there, of course, we go ahead and take the derivative in the next step of 6x raised to the 4, which is 24x cubed, times sine inverse of 6x raised to the 4. We also go ahead and deal with the derivative of sine inverse of 6x plus 4. And again, we know that the derivative of sine inverse of x on its own is just 1 divided by square root of 1 minus x squared, but everywhere where we see x, we replace it with 6x plus 4. And since 6x plus 4 is a function itself, we have to use the chain rule and take the derivative of the inside function 6x raised to the 4th separately. So for second term, that's what we have to handle. For this third term, of course, we just need to take the derivative of 1 minus 36x raised to the 8. And we see that using the power rule, we end up getting a negative 288x raised to the 7th. And then from that point, all we need to do now is just take the derivative of 6x raised to the 4, which we've already done. And that ends up being 24x cubed. And of course, you see that right here. And then, of course, I'm simplifying what I can at this point for this term. And then from there, it's just a matter of trying to rewrite everything to make it look nice. And so you see that once we do all of this, that this term and this term end up being exactly the same, so they cancel to 0. And our result here is that we just end up getting 24x cubed times sine inverse of 6x raised to the 4.